Hey, this is Math 105, section 6.3. We're looking at trig functions of angles using our triangle approach. Continuing. Okay, so we have POQ, which is a right triangle. Okay, it's labeled by the vertices, so B, P, O, and Q. So we start by placing it in standard position, because remember we know SOHCAHTOA, right? So we know we have sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent's opposite over adjacent. Okay, so where, if this is our angle here, theta, then opposite's here, adjacent's here, and hypotenuse is there, right, in our right triangle. Okay, and sine, cosine, and tangent. Okay, if we place it in standard position, it's going to look like this. The side adjacent to the angle is going to be on the x-axis, positive, and then the hypotenuse is going to be the radius, like the r, okay? And then the y is going to be, the opposite's going to be the y, up and down. So we kind of place it like that. Okay, and we place our triangle in standard position. And then our point P of xy is a point on the terminal side of our theta, okay, our angle theta, okay. So then the opposite side is y, okay. Adjacent side is x, and this is, we're talking about our triangle POQ, okay. And then we can look at r being the square root of x squared plus y squared using Pythagorean theorem. So our r is just a squared plus b squared equals c squared. So then we can see that sine of theta, I'll put this is my opposite over hypotenuse, right? Hypotenuse is the r. This is adjacent over hypotenuse, okay? And this is opposite over adjacent, okay? So we can see that our sine is going to be y over r, okay? Cosine is x over r, and tangent is y over x. So we're going to divide by r because that's our hypotenuse, okay, for the triangle, okay? And we can look at our other trig ratios the same way, okay? So now we can apply these to any angle, okay? It doesn't have to be on the unit circle. Okay, so for the triangle approach of our definition of trig functions, we can let theta be any angle in standard position, and pxy be the point on the terminal side, okay, the terminal point. Okay, so if r is square root of x squared plus y squared, okay, is the distance from the origin to the point pxy, then sine of theta is y over r, cosine of theta is x over r, tangent of theta is y over x. X can't be 0 because we can't divide by 0. And then the other trig functions just follow. Cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent, right? So those just follow. Okay, so this is what here's the setup now. Now we have, this is our standard position. We start here and we go to here, and here's our angle. And then we get this point here. And we just look at this distance, and that's going to be our r. Okay, distance from the origin to here. And then sine of theta is just y over the r. Okay, cosine of theta is x over the r. And tangent of theta is y over x. So we don't need to use a unit circle. We can just find this point, whatever it is, and just divide by the radius for y to get our sine of the angle, and just divide by the radius for x to get our cosine. And here, tangent, we don't need to use the radius because the r would cancel. If you think of sine over cosine, we have y over r divided by x over r, and the r cancels out there. Okay, it's important to note that the values of the trig function do not depend on the choice of the point pxy. In other words, if we go further out, let's say we do this, pxy, or we have p prime, x prime, y prime, it doesn't matter. These give us the same trig values, okay? Because what we have is similar triangles. If we use this inner point here, here's our triangle, okay? And if we use the outer point, here's our triangle. Those triangles are similar. They have just, one is just, we're expanding the triangle by multiplying all three sides times the same number. Okay, so it doesn't matter because we're going to divide by that r, and either way we'll get the same trig functions, whether we go here or here. So it doesn't matter how far out you go. Okay, and we kind of see that with the triangles because we're not just limited to a radius of 1 now. We can say the radius can be anything as long as you divide by that r. Okay, which r would be here, r prime would be here. Okay, so let's talk about how we evaluate the trig functions at any angle. Okay, we start by saying r is always positive. Okay. So it's simply the distance from the origin to the point pxy. Okay. So first of all, we say in quadrant 1, trig functions are all positive. Okay. If the terminal side is in quadrant 1, we're talking about where the terminal side is. Okay. That's because x and y are positive in this quadrant. Okay. If the terminal side is in quadrant 2, x is negative and y is positive. Okay. Okay, so we can say sine and cosecant are positive, and all other trig functions have negative values. Okay, in quadrant 2. Okay. Okay, and it sort of follows for the other quadrant. So in quadrant 1, all the trig functions are positive. Okay. In quadrant 2, I'm just going to show the ones that give us the ASTC. So sine is positive. Well, so is cosecant. In quadrant 3, tangent is positive. Quadrant 4, cosine is positive. Okay. So the negative functions are the other ones, and that's how we get our all students take calc, ASTC. So yeah, we know that cotangent is positive because tangent's positive, and secant's positive because cosine's positive, and the other ones would be negative. But I want to focus on these just so we can kind of see. Okay, if you're just talking about sine, cosine, and tangent, this is what you can use. You can use all students take calc, ASTC. Okay, and we're talking about just referring to sine, tangent, and cosine. Okay, so that's how we get the all students take calc. In the first quadrant, of those 3, all of them are positive. Of those 3 in the second quadrant, just the sine is positive. Okay, in the third quadrant, just the tangent's positive because sine and cosine are both negative, right? And then in the fourth quadrant, just the cosine is positive because sine is negative and also tangent's negative. So that's how we get this as all students take calculus. Okay, let's look at a couple examples. Cosine of 135 degrees. Okay. Cosine of 35 is minus x over r, so we're going to go 135 over here. Okay, see 45, 45, another 45 because it's 135, and we use minus x over y, or over r, sorry. Okay, minus x over r. Okay. Now we can say cosine of 45 is x over r. Okay, since these numbers are the same except the x changes, right? You have that symmetry across the y-axis. So cosine of 45 is square root of 2 over 2. So cosine of 135 degrees is minus square root of 2 over 2. And this should be degrees here. So should we put degrees there for those angles? Okay. I'm not talking about radians. Okay. So our cosine of 135 is minus square root of 2 over 2 because it's reflected this way, the x's. Okay. Okay, tangent of 390. Now remember, 360 is just a circle. So we can say 390 is the same as going 30 degrees, right? Because we do 360, we are back where we started. So 390 is the same as 30. So we say that those angles are coterminal. Okay, so the angles 390 and 30 degrees are coterminal. And that means that tangent of 390 is tangent of 30. Okay, since tangent of 30 is square root of 3 over 3, tangent of 390 is also square root of 3 over 3. Okay. Remember that tangent of 30 is 1 over square root of 3, but we have to rationalize the denominator to get that square root of 3 out of the denominator. So that's how we get that square root of 3 over 3. Okay, so that's how we get our tangent, and not 390. You know, same as that. Okay, let's talk about reference angle. Reference angle is just like your reference number that we did in chapter 5, except now we're talking about angle. So theta is an angle in standard position. Okay, that means the angle starts in the positive x-axis. Okay, the reference angle theta bar associated with theta is the acute angle less than 90 formed by the terminal side of theta in the x-axis. So basically, we're saying acute means less than 90 degrees. Okay, so it's going to be in the first quadrant. And basically, we're just taking the shortest path back to the x-axis, just like we did for t-bar. Okay, so that's what we say. We say formed by the terminal side of theta in the x-axis. We're going to go back to the x-axis as quickly as possible in the shortest path. Okay, so let's say your theta takes you to the first quadrant. Well, your theta bar, your reference angle, is going to be the same because you go back to the x-axis. It's the same distance, right? Okay. If your theta takes you to the second quadrant, then your theta bar is going to be this red here, okay, taking the shortest path to the x-axis. Okay. If your theta bar takes you to the third quadrant, then if your theta takes you to the third quadrant, your theta bar just is that angle there. Okay. And if your theta takes you to the fourth quadrant, then your theta bar is here. And remember, this is the same concept as reference number, t-bar, right? Except now we're using angle and standard position, using the chapter 6 concepts. But it's the same idea. We're going to use the trig functions for the theta bar to get the numbers for the trig functions for theta. Okay, so let's look at some examples, and we're going to look at radians and degrees. So first we'll find the reference angle for theta equals 5 pi over 3. So 5 pi over 3 takes us over here, And remember, 6 pi over 3 is a full circle, 2 pi, right? So we can say that our reference angle is just pi over 3, okay? Because another pi over 3 will take us at 6 pi over 3. Okay, so that's our reference angle for theta bar for this one. And we can see that our theta bar is 2 pi minus 5 pi over 3, which you could write as 6 pi over 3 is the same as 2 pi minus 5 pi over 3. Okay, so that's just a way to do that. Okay. Now for the second one, we're looking at 870 degrees. Okay. Basically, we can subtract two circles, right? Because 360 is not going to change anything, right? So we take two 360s out of there, we get 150. So angles 870 and 150 are the same. They're coterminal. They're going to put us to the same terminal side. Okay. So here's our 870. We go around the circle once, 360, 720, and then 150 will take us to the full 870. Okay, which means our theta bar is going to be 30 degrees. Okay, we take 180 minus 150, get 30 degrees. Because if this is 150, then the theta bar has to be 30. Okay, so there's our reference angle for theta bar. Okay, so here's the formal steps for evaluating trig functions for any angle. Okay, for any angle theta, we carry out the following steps. For the reference angle, find the reference angle theta bar associated with angle theta. Determine the sign of the trig functions of theta by noting the quadrant in which theta lies. And then the value of the trig functions of theta is the same, except for the sign, possibly, as the values of the trig function of theta. Okay, so it's the same thing we did with t and t bar in chapter 5, except now we're using theta and theta bar. Okay, so we already get the idea here. Okay, so let's look at sine of 16 pi over 3. This will be question part A here. Okay, that's right there. Okay, 16 pi over 3. Okay, so the angle 16 pi over 3 is coterminal with 4 pi over 3 because if we do we go around the circle once, that's 6 pi over 3. Okay, and then 12 pi over 3 would be circle around twice. Okay, and then another 4 pi over 3 would take us here. Okay, and we can see that takes us into the third quadrant. So we can see that our theta bar is going to be pi over 3. Because, 4 pi over 3, if we go 3 pi over 3, we're here, and another pi over 3 will take us there. Okay, so we're going to use the numbers from pi over 3 to get our sign. Okay. So our reference angle, theta bar is pi over 3. Okay. Since sine is negative in quadrant 3, y is negative, we have sine of 16 pi over 3 is sine of 4 pi over 3, because remember these angles are coterminal, which is the opposite of the sine of pi over 3, because we're changing the sign of the y. Okay, so we know that sine of pi over 3 is square root of 3 over 2, so sine of 4 pi over 3 or sine of 16 pi over 3 is minus square root of 3 over 2. Okay, and we're using pi over 3 as our reference angle. We're just checking the sign. When you go into the third quadrant, your y changes, your sign changes to the opposite. Okay, now we're looking at secant of minus pi over 4 for part B. So the angle minus pi over 4 takes us to quadrant 4, right? And our reference angle is just plus pi over 4, right? Because this is our theta bar is pi over 4, going back to the x-axis. Okay. Remember, our reference angle is always positive. Okay. Now, cosine of pi over 4 is positive, and so is cosine of minus pi over 4. So we're just going to use that number, square root of 2 over 2. Okay, so we can say cosine of minus pi over 4 is square root of 2 over 2. And so secant is just 1 over that. So secant is 2 over square root of 2, where we multiply times square root of 2 over square root of 2, and that's just going to give us 2 times the square root of 2 over 2, which is square root of 2. Okay, so that's how we get the secant there. Because the cosine is positive, the secant is positive, because remember, it's just a reciprocal. Okay, so we can say that the secant of minus pi over 4 is the same as the secant of plus pi over 4, because it's 1 over cosine, right? And we're just going from first quadrant to fourth quadrant. The x doesn't change, so that's just square root of 2. Okay, and remember, our reference angle is just pi over 4. Okay, the trig identities we've already looked at, but now we're going to look at these in the context of using theta instead of t. So our reciprocal identities, remember, our cosecant of theta is 1 over sine of theta. Secant of theta is 1 over cosine of theta. Cotangent of theta is 1 over tangent of theta. So those are reciprocal identities. Tangent is sine over cosine for theta. Cotangent of theta is cosine over sine of theta. And remember, sine squared plus cosine squared is 1. Is our identity using theta. If we divide both sides by cosine squared, we get tangent squared plus 1 equals secant squared. If we divide both sides by sine squared, we get 1 plus cotangent squared equals cosecant squared. So these Pythagorean identities, these just are all developed from this, because this one is kind of the fundamental one. We divide both sides by cosine squared, we get this one. We divide both sides of this by sine squared, we get that one. Okay? And way to remember these is that if you take tangent squared and add 1, you're going to get secant squared. And you take cotangent squared and add 1, you're going to get cosecant squared. Think of like your other trig functions, you know, besides sine and cosine. And then think of like the cos go together and the non-cos go together. Okay, and it's always tangent squared plus 1 and cotangent squared plus 1. So that's kind of a way to remember that. Okay, so let's go to a couple examples. Let's express sine of theta in terms of cosine of theta. Okay, so from our first Pythagorean identity, we get, you know, remember that's this. Sine squared of theta plus cosine squared of theta equals 1. And if we subtract cosine squared on both sides and take the square root, we will get sine of theta equals plus or minus 1 minus cosine squared of theta. So we're just doing some algebra here. But we have to do the plus or minus because, remember, the sign could be, you know, they could be the same sign or they could be the opposite sign depending on the quadrant. So we have to look at that. Okay. So it depends on the quadrant there, but that's how we would get sine in terms of cosine, okay? By, you know, getting sine by itself in this equation. Okay, right? We would subtract cosine squared on both sides, right? So we get sine squared theta equals 1 minus cosine squared, and then we just take the square root of both sides. That's how we get that, and that's plus or minus. So that's how we get the sine of theta equals plus or minus 1 minus cosine squared of theta square root. Okay, so if our theta is in the first or the second quadrant, y is positive, so sine of theta is positive. So sine of theta would be the plus. And if our theta is in quadrant 3 or 4, where y is negative, then our sine of theta is negative. So this is when we use the minus. Okay, so you use the plus for quadrant 1 or 2. Okay, put a plus there. And we use the minus for quadrant 3 or 4 for sine of theta. Okay. And that'll be, I'll put a plus there so we know that it's a plus. Okay. Okay. Okay, for our second example, we're going to look at tangent of theta in terms of sine of theta. So that's what we're doing there. Okay. Tangent, remember tangent of theta is sine over cosine. Okay. And we want to write cosine in terms of sine first because we don't want to use cosine, right? We just want sine. So cosine of theta is plus or minus 1 minus sine squared of theta, just, you know, by doing the same thing we did on part A, but doing it for cosine. Okay. Now, since cosine of theta is negative in quadrant 2, the negative sign applies here, so we're going to have the negative here. Okay. So tangent of theta is sine over cosine, which is sine over, now we substitute for cosine, we're going to use the minus there. Okay. And this was because we were in quadrant 2. Okay. So tangent of theta would be sine of theta over negative square root of 1 minus sine squared of theta, because, you know, again, cosine is negative here because we're in quadrant 2. Okay, let's talk about areas of triangles. Okay. Now I'm going to show you how we derive this, but for now we'll just go on faith on this. But the area of a triangle is 1/2 times base times height. Okay, where your base is this length here, and your height is how tall the triangle is. So it's not necessarily a dimension of the triangle. If it's not a right triangle, that height is just going to be it's going to be how tall it is. It's going to be a dotted line. It's not one of the sides. Okay, so this is our base here, and this is our height. Okay, and we just take 1/2 times base times height to get the area of the triangle. Okay, another way to do that is to look at AB sine of theta. Okay, so 1/2 AB sine of theta is another way to look at that area of the triangle. In other words, we don't need to find the height. Okay, what we can do is say this side is A and this side is B, right? We have two sides and we have the angle in between, right? And we can just do 1/2 AB sine of theta. Now, why is that? The reason is because your height, and your theta is here, right? Sine of theta, okay? Sine of theta is opposite, which is H, that's not hypotenuse, that H is the opposite side, over hypotenuse, which is the B, okay? And then we can say, okay, well, then if I multiply both sides by B, I get H equals B sine of theta, okay? So we can substitute it there for height, right? And that's how we get B sine of theta, okay? And then A is just our base, right? So we have area is 1/2 A times B times sine of theta. Okay, so and that's when you have one side, two sides, and the angle in between. So the angle has to be between those two sides. Okay, it doesn't have to be a right triangle, right? It could be any triangle. We just do the height here, and then we form a right triangle inside there, and we find the height by using sine of theta equals this h over this b, this side. Okay. All right, and then substitute in this half times base times height. So that's how we get this formula. So if you don't know the height, but you know two sides and the angle between, you can find the triangle, the area. Okay, so our area of a triangle is 1/2 base times height, or 1/2 AB sine of theta, where again we have AB as two sides of a triangle. Here's our A, here's our B, and it doesn't matter where your AB is. Okay, you can just do that. Okay, where you have the angle in between A and B. Okay, so it doesn't matter if B's on the base or not. It doesn't have to be. Okay, so there's our area of a triangle formula. Sides of lengths A and B and with included angle theta, that means the angles between them, is 1/2 AB sine of theta. Okay, so let's do an example. Let's say we have this triangle with this side's 3 centimeters, this side's 10 centimeters, and our angle is 120. Okay, so we want to find the area of that. Okay, so area is 1/2 AB sine of theta. Okay, our theta is 120. Our A side is 10 centimeters. Our B side is 3 centimeters. So it's 1/2 times 10 times 3 times the sine of 120, which is, remember, our reference angle is 60 degrees for 120. Okay, so remember the sine is the same when we go to 120. So if we go to 120, we're over here. Okay, theta 120, and then our theta bar is 60. But our sign doesn't change because our y is positive still in the second quadrant. So it doesn't matter if you have an obtuse angle, an angle that's bigger than 90 in your triangle, it still works. Okay, so we have 1/2 times 10 times 3 is 1/2 times 30 is 15 times sine of 60. Remember, sine of 60 is square root of 3 over 2. So this is 15 times square root of 3 over 2, which is about 13 centimeters squared. Make sure we use the right units here. We're talking about area, right? So we're going to use centimeters squared. Okay. So make sure that we identify the proper units when we're doing area.